Hello physicists! Last video we discussed one of the most important principles of two-dimensional motion, and it's that the components don't affect each other, and changes in those components of a vector don't affect the changes in another component. Which means we can now solve problems with two-dimensional motion very easily. Rather than focusing on the velocity vector as a whole, we can break it up into components. So when you throw a projectile in some direction, so let's say I throw this way. You give it a horizontal component and you give it a vertical component. Now, in real projectile motion, when you're just throwing it, there will only be an acceleration in the y direction due to gravity. There will be no acceleration in the x direction. Okay, when you're just throwing it and it's in the air, because gravity is the only force acting on it, on the projectile. And gravity, it's because it doesn't point, there's no other acceleration pointing sideways, no other natural acceleration, then the x component of the velocity actually stays constant throughout the interval, while the y component of the velocity changes due to gravity. And what this does is that it forces, in an ideal world, okay, and even in the real world, most projectiles, it forces the projectile path, the projectile's trajectory, to be a parabola, a graph of a quadratic. Okay, it forces the trajectory of the projectile to be a parabola, because if you remember from our kinematics equations, if this is the height and is the horizontal distance, you can easily show using the kinematics equations that the trajectory is a parabola. And now we have to make some adjustments to the kinematics equations, but not a lot. Because the components are independent, the x direction will have its own set and the y direction will have its own set. Okay? So for the x direction, in the most general case, so like in the case where there may be an acceleration in the x direction caused like by some like maybe propulsion or something along those lines. When in the most general case, these are the equations for the x direction. Notice how everything is subscripted with x. That's because we're only focusing on the x component of the acceleration, the x component of the velocity, the x component of the position, because we cannot put y components and x components together because they're independent. Similarly, we have a set of equations for y with subscripts of y. Subscripts of y. All right. Now, how do we actually use this? How do we coalesce these two together? How do we bring together these two if they're both independent? And there's one word, okay? And actually in the equation, there's one variable that's common to both directions, both dimensions, I should say, both components. And that is this one, time. There's no such thing as X time. There's no Y time. There's just time. Time is time. So that means that we have a common variable. We have a common variable. And because we have a common variable, we can easily solve and bring together the X component equations and the Y component equations to make one nice, simple equation relating the X and Y's together. So let's solve a problem. Let's see how we can actually put this into practice, because it's a lot easier to understand this when performing a practice problem. So let's say you're in a car. Let's say you're in a car and you decide to perform a not so smart stunt. For some random reason, you decide to perform a stunt. And you want to drive off a 50-meter cliff. You want to drive off a 50-meter cliff. Okay, you want to drive off a 50-meter cliff. And you drive off at a speed of... let's say 40 meters per second. So that's about like 45 or something miles per hour. And you're doing the stunt and you drive off a cliff at 40 meters per second. So my question is, how far from the base of the cliff will the car land and crash and get wrecked? How far from the base of the cliff? So let's see how we actually solve these types of problems. So over here, this is its initial velocity vector. This is v0. Now, question, does it have any initial y component? Okay, if you answered no, then you're correct. If you answered yes, a little suspicious. So if it has no y component, that means all the velocities are directed in the x direction. So we know that Vx0 is 40 meters per second. And because we're just falling off, it will always be 40 meters per second. So this will actually be quite important later on. Now, let's look at our equations. We have our y equations. Vfy equals v0y plus ayt. Delta y equals v0yt plus 1/2 ayt squared. We also have our x equations, but note that the acceleration in the x direction is 0. So you have vfx equals v0x, basically meaning that the velocity in the x direction is constant, and delta x equals v0x times t. Now, how do we approach this? This equation looks very attractive because it immediately gives you an expression. Ooh, my battery's low. Okay, immediately gives you an expression for x. It immediately gives you delta x. It immediately gives you this distance. However, we need time. And we can't use an x equation for that. Okay, we need to go to the y equation. And if we solve time from a y equation, we can apply the same time to the x direction, because the time is the same in both cases. Again, there's no y time, there's no x time. There's just time. So if we solve in the y component, we get the time there. We can immediately just plug it back into the x direction. Okay, so I'm going to show you what I'm talking about, right? So let's look at the y equation. We're not going to use the first one because it requires a final velocity, and we don't really know that. But we can use the second one. Because we know delta y, that is the height, 50 meters. We know AY because it's just G, it's falling. So AY will be G. So this becomes not so difficult. We're gonna use this equation, and because V0y is 0, the initial velocity is in the x direction, so there is no V0y. So this becomes delta y equals 1/2 gt squared, just replacing AY with G. Okay? And then we solve for t, and we get t equals square root of 2 delta y over G. And that becomes the square root of 2 times negative 50 meters over negative 9.81 meters per second squared. And what do we get as a result? Okay, what do we get as a result? We get, let's see, 100 divided by 9.81 and take the square root, and we get a time of 3.19 seconds. So it takes 3.19 seconds for the car to move from the top to the bottom. But at the same time, if the car moves from here in the y direction to here in 3.19 seconds, then it has to go from here to here in 3.19 seconds because it ends up over here. So it has to go from from this position to this position in the x direction in 3.19 seconds. So we found our time, and now we can use the second equation in the x direction. Delta x equals V0x t. So that equals 40 meters per second times 3.19 seconds. And that gets us this times 40 this times 40. My calculator is acting a little strange. Okay. We get 127.7 meters. 127.7 meters. So it travels far. And the more important thing is to realize how we solved for the common variable, the time, starting from the y direction and then applying that same time to solve for quantity in the x direction, because the y and x directions are related by only one variable, and that's time. Let's solve one more, okay? And this one's a classic. Suppose you were on a flat surface, okay? And you decide to launch a projectile at some angle theta, or the horizontal, okay? So here's the trajectory, okay? And we launch it at some initial velocity v0 with an angle theta above the horizontal, okay? My question to you is, what is the range? So how far will the projectile go in terms of v0 theta and any other important constants? How long will be the range? And perhaps the most important question, well, not the most important, but the most profound question, what value of theta will result in the maximum range? Okay, what value of theta will result in the maximum range? So let's see how we can do this. And this will require some algebra, but that doesn't really scare us at this point. Okay, so we have our initial velocity vector, v naught. How can we break it down so we can find v naught x and v naught y? Well, we can break it down into components, and we're given theta. So you can use trigonometry in order to find v naught x and v naught y. This side is a cosine. So this is v naught cosine of theta, and this is v naught sine of theta. So we have our initial x velocity is v naught cosine theta. Our initial y velocity is v naught sine theta. V naught sine theta. So what do we get? Okay, what do we get? We get v naught x and v naught y. And how do we approach this? Let's write our x equations and our y equations. So assuming that there's no acceleration in the x direction, which is true in this case, since it's following a normal projectile's path. Okay, so this is our x equation. And our y equations will include v naught y. Sorry, vfy equals v naught y plus at. And we also have delta y equals v naught yt plus 1/2 ayt squared. Okay, now we don't know vfy, but we can use, so we have to use the second equation. And then we can solve for time and plug it into the x equation. We're going to use the same strategy as last time. Now, what is delta y? We're not explicitly given delta y, but if we were to compare from ground level and we end up again on ground level, then a change in the y component and the height is 0. This is actually equal to 0. So we can write 0 equals v naught yt, so that's v naught sine theta t plus 1/2 gt squared. And what do we get as t? Now it's just a quadratic, and it's one of those factorable ones, which makes it very convenient. We have 1/2 gt, and what we're going to do is we're going to make this negative because g is negative. We're going to preemptively put the negative sign so we get a nice answer in terms of the magnitude of g. And we get this. Now, t equals 0 corresponds to when the object is initially starting. It's already at ground 0. But at this time, that will be this inner expression. So if we solve this and set that equal to 0, you get t is equal to 2 v naught sine theta over g. 2 v naught sine theta over g. Now, what is our range? Our range will be vx t. So that is equal to 2 v naught sine theta times v naught cosine theta over g. Now, that is our range. Now, what is our theta max? What is our maximum value of theta? Now, that involves taking a derivative. So I'm just going to simplify this. Oh, now my battery's really low. Okay, so now we have a simplified expression. How do we take the derivative? We just have to take the derivative of r with respect to theta and set that equal to 0. Okay? Now, in order to simplify things, notice how we have 2 sine theta cosine theta. We can use the trig identity. Yes, we do use these in real life. So we use this identity, 2 sine theta cosine theta, to rewrite the range as v naught squared sine 2 theta over g. Sine 2 theta over g. So there are 2 ways that you can do this. Okay. I'm going to show you the calculus way first. So in the calculus way, you take the derivative of the range with respect to theta. So we take the derivative of this expression. So we get 2 v naught squared cosine of 2 theta over g, and we set that equal to 0. We set that equal to 0, and that gets us 2 theta equals pi over 2, or pi over 2, and that gives theta equals pi over 4, which corresponds to 45 degrees. Okay, so that corresponds to 45 degrees. So we found this thing. We found the angle max using calculus. But there's a much nicer way to do this. Look at the expression at r. Now, if you're clever enough, you can see that there's already an upper bound for this expression. The maximum value of sine of any angle is 1. Sine of theta is always less than or equal to 1. So whatever value of theta makes this expression, makes sine of 2 theta equal to 1, that will automatically be the maximum. So sine of pi over 2, so we already know that sine of pi over 2, excuse me for just a moment. So we already know that sine of pi over 2 has to equal 1. So we already know that sine of pi over 2 has to equal 1. So that means 2 theta has to equal pi over 2. So we get the expression theta equals pi over 4, the exact same answer. So regardless of which method you use, you should get the same answer, 45 degrees. So for a flat surface, this is the angle that gives you the maximum range. So if you're aiming cannons at things, you might want to consider an angle of 45 degrees, right? Thanks for watching. If you have any questions, just comment below, right? And the main concept of solving any two-dimensional motion problem is just relating the x component to the y component and realizing that the motion is independent, but they can still be connected through this variable of time. All right, thanks for watching. See you next time.